right? So that's my beam. So what you're going to see is a three-dimensional animation of a beam with a rectangular cross-section. Right, that's the rectangular cross-section. And passing through the center line of the beam, this axis here, right? I don't call it center line. This axis is a special name that we'll explain in a minute. It's called a neutral axis. 中性 neutral axis. And what we are going to see is we try to bend the beam. Of course, the beam originally it's a straight member, but when you bend it, of course, you bend it into sacking. So the beam is going to bend into sacking. Right? And then what we are going to look at is we try to zoom in from the elevation view. So we're going to look at the beam from this angle, right? Elevation. So you're going to look at it at the front and try to zoom in this little part here. We try to zoom in and look at this part at the center. Okay, so this is the elevation view. Right, so we look at it from this way. If you look at it from this way, then that's what you are going to see. And the next figure here is the zoom in of this little part here. So you try to zoom in and look at this center part here. Right, so what we're trying to do is to bend this beam. Right, bend it like this. Right, originally straight. So we bend it like this, and we're zooming at this part. Right, the center part here. Right, like that. And what about these two things? These two represent, on the left side, that's a rotation, on the right side, that's another rotation. So if you have a beam like this, right, you try to bend your beam into sacking. How do you do that? Your left hand rotate like this. So to me, this is clockwise. And my right hand is rotating in the anti-clockwise. So this one clockwise, this one anti-clockwise. Together, right? The beam will bend into sacking like that. Okay, that's what those two symbols mean. Right? You try to bend your beam like that. So, as I said, we try to look at the elevation view in particular and zoom in this part and see what happens. Okay, so this is what we're going to look at. The animation. Right, so that's my beam in 3D view, and we try to rotate left hand and right hand at the same time, and the beam will deflect into sacking. We try to look at it from the elevation view, so we look at it from this side, this center part here. Okay, so we zoom in. Those lines doesn't mean anything, right? Those lines are just for you to easier for you to see something that is going to happen, right? So originally, before you bend, all the lines are straight. 你咪咬彎嗰條邊之前，全部嘅線都係直嘅。Right? So this line here the top surface of your beam. The bottom line, of course, represents the bottom surface of your beam. Originally, all lines are straight. Okay? And then I try to, at the center line, that is the neutral axis. Okay? And then I try to put some dots along these two sections. So what you should focus on is you pay attention to the distance between each pair of dots. 每兩點之間嗰個距離，呢個水平嘅距離。Before bending, the distance between each pair of dots are exactly the same. 未有 bending 之前，佢哋每一對嘅距離都一樣，完全一樣。But when you bend your beam, look at the distance between each pair of dots and how does it change. So what you see at the top surface, 最頂嘅 those two dots comes closer, 近咗。And the pair at the bottom, they go further away from each other. 佢離得遠咗。So what does that mean? That implies the material between these 2 points shortens. 即係呢兩點之間嘅物質係短咗。And the material between these two dots at the bottoms, they elongate, 拉長咗。In other words, there must be compression at the top. There must be tension at the bottom. Pay attention also to the direction of compression. Remember what we said at the start. Compression, the direction of the compression is the same as the direction of the shortening. 向呢邊係縮短咗，所以個 compressive force is in the same direction of the shortening. Okay, now pay attention to this pair of dots, which is a little bit lower than the top surface. What happened? They also come closer, 都係近咗 but not as much as the top one. 相對頂嗰咧冇近咁多，不過都係近咗。Pay attention to these two dots. It's a little bit away from the bottom surface. And the distance between them is getting further apart, but not as much as the bottom. 都係拉遠咗，不過冇底嗰個拉得咁遠。So what does that mean? That means there's also compressive force here. But the compressive force is lower than the top surface. At the bottom, you have tension force. Here, you also have tension force, but the tension force is a bit smaller than the one at the bottom surface. Okay? So this is what we can observe from the animation. And this picture is captured, this screen is captured on your handout. If you flip to the next slide. This is what you see. So this one, it's before bending. So this is before, this is after. So that's before bending. That's after. So this is an elevation view. Remember that's an elevation view? So the beam actually bends like this. Right, this is what happened. This is after. This is original. After. the elevation view. So this top line here represents the top surface. This bottom line here represents the bottom surface. And the neutral axis is right at the center, passing through the center. Okay? So this line here is my top surface. That line here is my neutral. So we'll explain in a minute why it's called neutral. And the bottom, that's the bottom surface. Right, that's before bending. After bending, that's what we said. Compressive at the top. Top half. Above the neutral axis, everything in compression. Below the neutral axis, everything in tension. But the maximum compression is at the top. So this one is maximum compression. Maximum C is at the top. This one is also compression, but it's a bit smaller than the maximum value. So it's still C, compression. So I just put this little c here, just to say this little c is a bit smaller than the maximum. Below the neutral axis is tension, this side, tension. So what happened here? This is little t, it's tension. But it's a bit smaller than the maximum tension at the bottom. So at the bottom, that's my maximum T. So if I describe like this, it's okay, but it's not the best way to describe. The best way to summarize what we can observe from this animation is it's better to sketch it. So I can summarize this by just using one figure. It's not something difficult. At the top surface, what I said is maximum compression. So I represent this like this. This is my maximum compression. Where's the neutral axis? Neutral axis somewhere at the center. So that's my neutral axis. At the bottom surface, there's a maximum tension. So I represent it like this. Right? Compression. So you try to compress it. Tension. You try to pull it like that. Below that, you still have compression, but a bit smaller. And further below, even smaller. Further below, even smaller. So it gets smaller and smaller and smaller, 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 until at the neutral axis, there's no compression. Below it, that's maximum tension. And then as it goes up, the tension goes smaller, 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 until at neutral axis, there is no compression, no tension. So that's why it's neutral. So at this end, A, neutral axis, C, or T, both of them, it's zero. That's why it's called neutral. So I can join these 2 points together. So the compression gets smaller, 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 until zero. Same thing for the tension side. So the tension gets bigger and bigger towards the bottom. Like that. This is my T, this is my C. So this figure summarizes everything on the animation. Okay? Right, so what's next? So we can see, oh, by the way, bear in mind, this beam is now under sacking. Okay, so I should put a word here. My beam is now under sacking. So if you have sacking, if a beam is under sacking, then now I understand part of the beam, the top half of the beam, is actually in compression. The bottom half of the beam is actually in tension. So half compression, half tension. That is sacking. And then, same question. What about if it is hawking? Right? Remember, this is sack. This is hawk. If hawking, then you just reverse everything. You just flip the diagram upside down. If it is hawking, then the top half tension, bottom half compression. 你即係調轉個頭嚟睇啫嘛。That's hawking. Second. Okay, so bear in mind what we have drawn here is for a beam under sacking. If you want to know what happened to hawking, you just reverse everything upside down. Now, one last step. So on the top half of the beam, I have compression everywhere. It's a distributed force, is it? It's everywhere on the top half. But it's not uniform, my penguin. It changes. So if I add all these compression together, I got a total compression for the top half. So I can represent like this. I have a big total C. I just add all the compression together. So I should have a total compressive force acting somewhere in the top part. So in the bottom part, I can add all the tension together. You add all the tension together. So I have a total T somewhere in the bottom half. So I can represent like that. So that's my total T. And then the next step is I can use something I learned before in equilibrium, in the chapter of equilibrium. So what does equilibrium say? This beam, of course, is in equilibrium. So what that means is the sum of force in the horizontal direction, this is horizontal direction, must be zero. Sum of force in the horizontal direction, it must be zero. So in other words, C must be the same as T. The magnitudes are the same. Of course, directions are opposite. They cancel out. So that's what equilibrium says. Horizontal equilibrium. But then that means I got two forces equal in magnitude, opposite in direction, and they are separated by a distance, whatever, little z. Okay, they are separated by a certain distance. So that's something again what we have said in week 9. If you have something like this, two forces equal and opposite in direction. So equal in magnitude, opposite in direction, acting like this. What would you get? A moment. Right? That will give you a moment. a moment because of the C and T. I have a moment. Remember, moment is force times distance. So which force? C or T? Doesn't matter. Why doesn't matter? They are the same. So you can use C or T times the distance between them. You got a moment on this section coming from bending. You got a moment coming from bending. So this is your bending moment. This is exactly your bending moment. So that is what we said before the break. Elongation is due to tension. Shortening is due to compression. Bending is due to bending moment, and bending moment causes bending. Okay? So that's what we mean by bending moment. Yeah, here. That's what we mean. Right? Elongation, tension, shortening is due to compression. Bending is due to bending moment. Or you can say bending moment causes bending. Alright? Right, so we'll continue with a few more slides before we come to the in-class exercise. So the important thing about the coming slides is you try to learn how to sketch the deflected or deformed shape of your beam. And from the deformed shape or deflected shape, you can tell where's the tension and where's the compression side and where's the main reinforcement. Right? Remember we're talking about reinforced concrete. So first example is just the simplest case, just a beam, support on two sides, and you got a load acting right at the center, pushing down, so that's simple enough. Like that, right? So it will bend like this. So that's sagging. So you can immediately identify from the deflected shape. Right? So this is the deflected shape. Two supports. Right, so that's tacking. So tacking means the top half compression, bottom half tension. That's the cross section. And that's why you put reinforcement at the bottom, to take out the tension. And of course, in the cross section, if I make this cross section, if I redraw this cross section a bit bigger, right, you should have known that. Of course, the reinforcement, you cannot put it right at the bottom surface. You need to cover it. That piece of concrete is called concrete cover. Everybody should have learned this in your material or contact courses. Right, so that concrete cover is to protect the reinforcement against fire, against corrosion. So how thick is the concrete cover? Well, at least you should be about 20 or 25 millimeters should be the minimum. 20 to 25 millimeter, it's about the minimum, usually. But it can go up to 70 or 75 millimeter thick if you have a pile. Right, so it changes. So this diagram is saying the top half, this dotted line of course is your neutral axis. Right? And then the top half of your compression. The bottom part is tension. The only difference is instead of drawing compression and tension on the same side, this figure, I just draw the tension on the other side. But it's the same thing, no difference. But one thing you should bear in mind, above the neutral axis, so let's say this is my neutral axis, everything is in compression. Fine, okay, this is a piece of concrete, so concrete in compression is good, no problem. Below the neutral axis, everything is in tension. So what happened to concrete when it is in tension? It cracks. Why it cracks? Because it's weak. It's very weak in tension. It cannot take much tension. So in other words, in practice, we usually ignore this part of concrete. So I would just draw, ignore concrete in tension.